great, but
All right. You ready?
Yeah.
Okay. So I'll have to apologize to my subscribers for the interruption. All right. So we're talking about psi. So psi S is solute potential. Psi P refers to pressure potential. Pressure potential. Okay. All right. So for the most part, when we can determine psi, which is the overall water potential, so you don't get confused, water potential is the psi without a subscript. When we know the psi, for example, inside of a cell and the psi outside of a cell, we can make a prediction about which direction osmosis is going to occur. It will occur in the direction of high to low water potential. So, the equation that you will see and that we're going to use mainly has to do with psi S. So psi S is equal to negative I CRT. Negative I CRT. All right. So, these four variables go like this. So, I. So, I is known as the ionization constant. The ionization constant. Okay. What this basically means is whatever solute is involved, if it ionizes in water, that'll change its ionization constant. Right, so let me give you an example. So let's take sodium chloride. Right, sodium chloride is a common solute, but when it gets dissolved into water, we know that hydration shells, they form around sodium and chloride. Right? And so these two actually get split up into sodium and chloride in water. Right? So what we would say is that the ionization when sodium chloride is the solute, the ionization constant is 2. Right? Because we have 2 ions that come about when you dissolve it into water. So your I value is 2. Okay. Typically, you're going to see either an I value of 2 or an I value of 1. So an example of an I value of 1 would be something like glucose. Right? So glucose, a sugar, or sucrose, a disaccharide. Right? When it's dissolved into water, it doesn't split up. It remains 1. And so its I value, even in water, doesn't change. So its I value is 1. Right? Sometimes they'll throw at you a molecule that ionizes into 3 parts, and so simply your I value will be. But for the most part, it'll be I equals 2 or I equals 1. Okay. Your C value. Your C value is concentration. Right? This is our concentration of solutes. And we use, bless you, molarity. So the units for this are going to be molarity, which is equal to the moles of solute divided by the liter, 1 liter of solvent, which is typically water. moles over liter. Okay. Our R value. Our R value is a pressure constant. Pressure constant. This is always going to be the same thing. This value is 0.0831 liter bar divided by mole Kelvin. Because why not have all the units possible? So liter bar mole Kelvin, for that same constant will always be 0.0831. And then lastly, T is our temperature. So our temperature is going to be in kelvins. In kelvins, the way that you do a change from Celsius is you take your degrees Celsius and you add 273. And that will put your temperature into kelvins. If you do it with Celsius, you get the wrong answer. You always got to convert it to kelvins. Okay, questions? So that's how you calculate our solute potential. That's the bulk of the work. A quick note about pressure potential. So pressure potential if you are referring to an open container, or an animal cell, side P will usually be 0. So if it's an open container or an animal cell, your side P will normally be 0. However, if a closed container or plant cell, side P will not be 0, but it will often be provided. Okay, and that has to do with the cell wall. So the cell wall in a plant cell, remember they don't have them in animal cells, the cell walls can actually sustain a good amount of pressure. And so what will happen is even if water fills a plant cell, the cell wall will kind of keep it contained, and pressure will become a factor in addition to solute potential for the water. But when that comes up, we'll talk about it. Typically, though, side P will be 0. Okay. Any questions? All right. To wrap this up, let's do one sample, and then you're going to get lots of practice today. So, we want to calculate solute potential of a 0.2 molar sucrose solution at 22 degrees Celsius. Go ahead and work with your neighbor. Take, say, a minute and a half. See if you can calculate what's the solute potential of a 0.2 molar sucrose solution at 22 degrees Celsius. So give it a shot, and then we'll come back and do it together. That bar, it's the units, and all the units on the side.
Every science teacher obstacle. So Miss Gordon's asking me to please check your storage. Yeah, I don't.
Okay.
I don't know.
Yeah, I'm not sure. Yeah, I'm sorry. Okay. All right, let's bring it back together. 3, 2, 1, 0. All right. So, we're looking at a sucrose solution. So sucrose is a sugar. Sucrose has an ionization constant of what, Brian? That's a sugar. 1. Right. So anytime you see a sucrose, fructose, glucose, sugar, it's never going to break apart, and so your ionization constant will be 1. Okay. Our concentration is what, Sophia? 0.2 m. So m, just so you can remember. So m is just the shorthand of molarity. M is the shorthand of molarity. So we've got 0.2 moles over liter. We have our pressure constant. Okay. And then what is our temperature? Tyler, what'd you get for your temperature? 295, right? So 22 plus 273 is 295 Kelvin. Okay. And if you go through, all of the units will cancel except for 1. So let me write this out for you. Let me change this real quick. So this is moles over liter. It's the same thing. osmolarity just so you can see the units canceling out. So if you look right here, we have liters at the top here and liters at the bottom. Moles at the top, moles at the bottom, kelvins at the bottom, kelvins at the top. So it leaves bar. So, bless you. Our psi value negative 4.9. Okay. That's our solute potential is negative 4.9 for this particular solution. Bars. Thank you. Bars. So, I got a question. What the heck is a bar? So, bars are just the units of psi. It has to do with, it's related to pressure. You don't really need to know why they call it bars, but anytime you see that unit, it's referring to either solute potential, water potential, or pressure potential. They all use bars. Okay. All right. Questions? So, if you imagine, just for a second, right? Imagine that you have a beaker full of the solution that's described here, right? So imagine you have a beaker full of this solution. You have a 0.2 molar sucrose solution, okay? And inside this, let's say you have an animal cell. With a psi equal to negative 1. Okay. So imagine you have an animal cell inside of this sucrose solution, which we know has a psi s equal to negative 4.9 bars. Okay. So notice with the sucrose solution, we need to calculate the psi. Okay. So psi s is just one component. The other component is psi p. Okay. This is an open container. Psi p is going to equal to what? 0. So in this case, our psi, I'll do it over here, is equal to negative 4.9 bars because the psi p is equal to 0. Do we have any questions on how I got that? Okay. So now we have our two psi values. Turn to your neighbor. Is water going to diffuse into the animal cell or out of the animal cell, considering the psi values for both? Look at our very beginning. Goes from high water potential to low water potential. All right. So, before we talk about the answer, let's make sure we're clear. So, inside of the animal cell, the purple circle, right? The psi value has already been given to you as -1 bar, right? The psi value of the solution in the open container is -4.9 bars. Okay. Which psi is larger, Adriana? Inside of the animal cell or in the solution? Which psi value is larger? Inside the cell, right? -1 is higher than -4.9. Don't get confused by the larger numbers. Remember, it's a negative number here. So in this case, Michelle, is water going to diffuse from the solution into the animal cell or from the animal cell into the solution? Animal cell into solution. Great. So we'd expect water to diffuse outwards. Right? Because we're going from high water potential to low water potential. Okay? Which is what we said at the very, very beginning. High water potential to low water potential. Okay? All right. Questions? Okay. So we're going to get a lot of practice with this today. Again, the more you do this, you realize that it's pretty straightforward. It just can get a little bit weird with the negatives and some of the variables. But before we get into practice, let's take a 2-minute break, stand up, stretch, and then we'll go back. Yeah.
First one. Why did you see that? Why haven't seen that? I'll have that mine. Don't even try to read it, don't play. As a comment. Just because if you take a grade,